Today in class we looked at implicit differentiation. First we reviewed the derivatives of tangent of x, which is secant squared x, sine of x, which is cosine of x, e to the x, which is e to the x. Next, we wrote inverses for three functions, the tangent of x, the sine of x, and e to the x. Remember, to write an inverse, you swap x and y, and then solve for y. So in red, I've swapped x's and y's, and I'm going to solve for y by writing arctan of x. Today we'll find the derivative of the arctan of x. The inverse of y equals sine of x, y is equal to the arcsine of x. Today we will find the derivative of the arcsine of x. Last function, y equals e to the x. Solving for the inverse, y equals the natural log of x. Today we will find the derivative rule for the natural log of x. In order to do this, we need to use something called implicit differentiation. Up until now, we've done explicit differentiation, meaning we have always had a function of x. So, you had 3x squared plus the cosine of x. Y is in terms of x. Sometimes we will be given a function that is not written y in terms of x. This relation, for example, is an ellipse. And we can actually solve this equation for y. So we could differentiate y in terms of x. But sometimes it is difficult, inconvenient, or completely impossible for me to solve an equation for y. Example number 1, we could solve. If I look at example number 2, I'm going to be hard pressed to figure out what y is equal to. Maybe a higher power can, but I can't. So we're going to do something called implicit differentiation. 3 examples here. In the first example, what we're trying to integrate is really the function y equals x cubed, or f of x equals x cubed. You know how to do that using the power rule, but what's important to note is that the variables inside the function match the variable with which we are taking the derivative with respect to. So, x cubed, derivative with respect to x, 3x squared. In the next example, kind of looks similar. We have the derivative, this time of y cubed, with respect to x. These variables do not match. Now what we must remember is that anytime you see a y, you have to think of it as a function of x. So the derivative would be, the derivative of y with respect to x is f prime of x. If we take a look over here, they're using the power rule to take the derivative of y cubed, and we get 3y squared. But remember, if y is a function of x, then we must also multiply by the derivative of y with respect to x. We just applied the chain rule. Looking at this another way, the derivative of f of x cubed would be 3f of x squared. Since f of x is some function of x, but its derivative is not 1, I must multiply by the derivative of f of x, which you'll see as f prime, or dy dx. Okay, last one. We have two pieces of a function added together, two terms. In the first term, the variable x matches with respect to x. In the second, we have a y variable. It does not match. So we have to take the derivative in two parts. We're going to take the derivative of 2x to the fifth, getting 10x to the fourth. But the derivative of 3y will be just 3 times the derivative of y with respect to x. Let's take a look at two examples. Example number 1. Negative 3y squared is equal to x to the fourth plus 5. We're going to differentiate both sides with respect to x. On the left side, my variable does not agree. Y and x are different. I'm going to differentiate using the power rule, getting negative 6y to the first power. Y is a function of x, so I must multiply by the derivative of y with respect to x. On the right-hand side, we have a function of x. The variables agree. We're just going to use our power rule and be done. Now, I do need to solve for dy dx, and so I'm going to do that by dividing both sides by negative 6y. Reducing, we'll get negative 2x cubed over 3y. The next example. Again, on the left, the variables do not match. We're going to differentiate y squared as 2y times the derivative of y with respect to x. I just applied the chain rule, remembering that y is some function of x that does not have a derivative of 1. The derivative of negative 7y is negative 7 times dy dx. The right-hand side. Oh, here we have a chain rule problem. So the outer function is the cosine of x. The derivative of cosine of x is negative sine of x. The inner function is x cubed. The derivative of x cubed is 3x squared. Remember the chain rule says, take the derivative of the outer function composed with the inner function times the derivative of the inner function. The chain rule just happened. So let's write our derivative for cosine of x cubed. It will be negative sine of x cubed times 3x squared. Simplifying a little bit here. On the left, I'm going to factor my dy dx from each of my two terms, 2y minus 7. On the right, I'm just going to move this 3x squared to the front, combine it with that negative 1 that's in front. So negative 3x squared sine of x cubed. To solve for dy dx, we will divide both sides by 2y minus 7. Alright, so let's take a look at our goal for today. We wanted to solve for the derivatives of arctan of x, arcsine of x, and natural log of x. We're going to do that by rewriting each of these functions, y equals arctan of x, as x in terms of y. So x equals tangent of y. We're going to differentiate both sides implicitly. The first, on the left side, the variables match, so the derivative of x with respect to x is 1. The derivative of the tangent of y with respect to x is secant squared y dy dx. We're going to solve for dy dx. We'll get 1 over secant squared y. I'm going to write that as cosine squared of y. Now let's go back to our definition that x is equal to the tangent of y. Let's make a picture of this angle y. Angle y, the tangent of angle y, is x over 1. I'm going to label my triangle, x on the vertical, 1 on the horizontal, and I'm going to find the hypotenuse, which is going to be 1 plus x squared, underneath the square root. Now, what is the cosine of this angle? Why do I want that? My derivative is the cosine of y squared. I have a picture of angle y. I know the cosine of angle y. I'm going to square it. 1 over the square root of 1 plus x squared, squared, turns out to be 1 over 1 plus x squared. That is the derivative of the arctangent of x. You no longer have to do this process, you just have to know this rule. All right, let's do the same thing with arcsine of x. We're going to rewrite y equals arcsine of x as x equals sine of y. We're going to differentiate both sides. The derivative of x with respect to x is 1. The derivative of sine is cosine of y times dy dx. Solve for dy dx. We get 1 over the cosine of y. That is the same as the secant of y. Let's go back to our definition of x equals the sine of y. Let's draw a picture of this angle. The sine of y is x over 1. X is the opposite side. 1 is the hypotenuse. The adjacent leg is 1 minus x squared under the square root. Now remember, cosine and secant are reciprocals. So if I find the cosine of y, I will take its reciprocal to find the secant of y. So what's the cosine? Adjacent over hypotenuse, that would be the square root of 1 minus x squared over 1. But the secant is the reciprocal of that, so that's 1 over the square root of 1 minus x squared. This is the derivative of the arcsine function. Okay, last one, the natural log of x. We're going to rewrite the natural log of x, y equals natural log of x, as x equals e to the y. We're going to differentiate both sides. We're going to get 1 equals e to the y dy dx. We're going to solve and get 1 over e to the y. Now this one, we already know e to the y is defined as x. So we can just replace e to the y with x, and we get 1 over x. All right, let's do some examples. First of all, you have your derivative rules. You just need to know these now, but now we're going to use them in some examples. Okay, so my first example is the arctangent of t squared. There is an outer function, arctan. There is an inner function, t squared. This means what we're using is the chain rule to find this answer. Okay, so remember the chain rule says we take the derivative of the outer function composed with the inner function times the derivative of the inner function. Okay, so I need my derivatives. Inner function is 2t. The derivative of arctan is 1 over 1 plus x squared. So my derivative of the arctan of t squared should be 1 over 1 plus t squared squared times 2t. Our answer then is dy dt is 2t over 1 plus t to the fourth. All right, next example is also a chain rule problem. My outer function is the arcsine of x. The derivative of the arcsine is 1 minus x squared underneath the square root and in the denominator, so 1 over the square root of 1 minus x squared. My inner function is the tangent of theta. The derivative is secant squared theta. This is also a chain rule, so we're going to do the same thing we did before, f prime composed with g of theta times g prime of theta. All right, taking the derivative then, we have 1 over the square root of 1 minus g of theta squared. G of theta is tan theta. We're going to multiply that by the secant squared of theta. And I'll just clean it up a little bit. Secant squared of theta in the numerator, in the denominator, the square root of 1 minus tan squared theta. If this were a plus sign, we could do some simplification with a Pythagorean trig identity, but it's not. Okay, I'm going to run out of time for the last example here. Give it a try, and we'll see you next class.